Greetings everyone, my name is Hazim Yahya bin Doliadi, and today I will be presenting Chapter 2 on Optimum Cross-Section Rectangular as part of my Practical Oriented Component, POC. Before we dive into the topic, I would like to introduce my dedicated team members who have worked tirelessly alongside me. There are Ethan Bandang Brow, McQuinn Kuehl, Daniel, and Alistair. Together, we have collaborated to ensure that our work on optimizing the cross-section of rectangular channels is thorough and comprehensive. I am grateful for their support and contributions, which have made this presentation possible. Today's presentation will cover several key points. We will begin with an introduction to the topic of optimum cross-section rectangular, followed by a discussion of the objective behind optimizing rectangular open channels. Next, I will provide detailed information on the relevant concepts and variables. We will go through the steps to solve for the optimum cross-section dimensions. After that, there will be a Q&A session. For introduction of this chapter, hydraulic engineering, optimizing the cross-section of an open channel is essential for maximizing hydraulic efficiency. The focus is on selecting a cross-sectional shape that minimizes frictional losses and maximizes flow capacity. For rectangular open channels, the primary goal is to determine the dimensions that minimize the wetted perimeter for a given cross-sectional area, thereby enhancing the hydraulic radius and overall efficiency. Understanding the relationship between the width and depth of the channel is crucial for achieving this optimization. Today we will explore the principles and calculations that guide this process, providing a clear framework for designing hydraulically efficient rectangular channels. Then, the objective of this presentation is to determine the optimal dimensions for a rectangular open channel to achieve maximum hydraulic efficiency. This involves minimizing the wetted perimeter for a given cross-sectional area, thereby enhancing the hydraulic radius and overall flow capacity. By understanding the relationship between the width and depth of the channel, we aim to provide a clear framework for designing hydraulically efficient rectangular channels. We're going to learn some information in terms of key variables in this chapter: width of the channel, B, depth of the channel, D, cross-sectional area, A, wetted perimeter, P, hydraulic radius, R. These variables are crucial for determining the most efficient dimensions of the rectangular channel to maximize flow capacity and minimize frictional losses. We move into steps on solving the question. First, sketch a rectangular channel to visualize its width and depth. Then derive the basic equations for the cross-sectional area and the wetted perimeter. Next, use these equations to calculate the flow rate, Q, using Manning's formula. Replace the area and perimeter in the flow rate equation with the ones derived, and solve for the depth. Finally, sketch the optimized cross-section where the width is twice the depth to show the most efficient design. After learning the steps of solving, there is a sample question that we can refer on how we're going to answer and write the exact steps to solve the optimum cross-section. So these are questions we're going to answer right now. From the question there, a rectangular channel 6.5 m wide and 1.5 m depth has a bed slope of 1 in 1200. The channel used to collect surface runoff from nearer residential area. Determine the discharge of channel when Manning's roughness n equals sine 0, 0.17. Due to the increase of surface runoff, the capacity of the channel must increase by 25%. Estimate the new flow depth and width of the channel if the optimum cross-section is used. To answer the question, we need to apply the steps into this question. To determine the area of the rectangular channel, we use the formula A equals sine B times D. The perimeter is given by is P equals sine 4D, and we know P equals sine 9.5 meter, so solving for D gives D equals sine 2.375 meter. The hydraulic radius is calculated based on formula. The value is 1.026 meter. With B equals sine 2D, we find B equals sine 4.75 meter. Resulting in using Manning's equation, we can determine the discharge Q of the channel, given the Manning's roughness coefficient and the slope. If the channel capacity increases by 25%, the new discharge is 125%. From that, we can determine the new discharge of the rectangular channel. We solve the answer easily by fully the steps that had we learned earlier. Thus, this steps of solve helps to answer this typical answer. Hence, we must practice a lot to master this kind of questions. We must know the way to answer this question so we can have the full marks. Last but not least, the conclusion PF this topic is the optimum cross-section for a rectangular open channel in terms of hydraulic efficiency is achieved when the width is twice the depth, B equals sine 2D. This ratio minimizes the wetted perimeter for a given cross-sectional area, thereby maximizing the hydraulic radius and the flow efficiency of the channel. This ratio minimizes the wetted perimeter for a given cross-sectional area, thereby maximizing the hydraulic radius and the flow efficiency of the channel. This approach ensures channels handle increased flow rates while minimizing frictional losses.